Welcome to another example of solving linear programming problems using the simplex method. The special case that we'll look at in this example is that of unrestricted variables. So the problem at hand is use the big M method to maximize z is equal to 3x1 plus 2x2 plus x3. Subject to the constraints 2x1 plus 5x2 plus x3 is equal to 12, 3x1 plus 4x2 is equal to 11, x2 and x3 are greater than or equal to 0, while x1 is unrestricted. So what this means is that x1 can take any value. It can be negative, 0 or positive. So now the first step in solving linear programming problems using the simplex method is to construct an LP model of the problem. Now in this step, we have to convert the given word problem into an LP model. In this example, we already have been given the LP model. However, before moving to step number 2, we have to confirm that two conditions are met. The first condition is that the right hand side of each of the constraints should be non-negative. So here the right hand side of the constraints is non-negative. The second constraint is that each of the decision variables of the problem should be non-negative. This condition is not met because x1 can be negative because x1 is unrestricted. Now the condition to solve the LP model using simplex method is that the decision variables should be greater than or equal to 0. So if x1 is unrestricted, we will not be able to solve this problem using the simplex method. So in order to solve this using simplex method, what we'll do is we'll replace x1 with two variables, x1 dash and x1 double dash. Both x1 dash and x1 double dash are supposed to be non-negative, and their values will be such that x1 dash minus x1 double dash will be equal to x1. So now we can replace x1 in these equations by x1 dash minus x1 double dash. So let's do that. So the objective function is z is equal to, now 3 times x1. x1 is to be replaced by x1 dash minus x1 double dash. So this will become 3 multiplied by x1 dash minus x1 double dash. So this will become 3x1 dash minus 3x1 double dash. So z is equal to 3x1 dash minus 3x1 double dash, and the remaining will be as it is, so plus 2x2 plus x3. Now same thing for the constraints. We'll have x1 replaced by x1 dash minus x1 double dash. So constraints become 2 times x1 dash minus 2 times x1 double dash plus 5x2 plus x3 is equal to 12. And the second one becomes 3x1 dash minus 3x1 double dash plus 4x2 is equal to 11. And now x2, x3, x1 dash, x1 double dash are all greater than or equal to 0. So now that the second condition is being met, that is all the decision variables are greater than or equal to 0, We can now proceed to step number 2, which is to standardize the problem. So I have noted down the revised LP model here in red. Now we'll move to step number 2, which is to standardize the problem. So generally in step number 2, we have to convert the inequalities, that is greater than or equal to or less than equal to, into equalities, that is equations. In this example, both the constraints have a equal to sign, so we don't have to add a slack or surplus variable. However, when we proceed to the subsequent step where we'll have to find the basic initial feasible solution, we'll have to make x1 dash, x1 double dash, x2 and x3 equal to 0 because these are the decision variables. So then we'll not be able to get any basic initial feasible solution. So in order to get the basic initial feasible solution, we'll add artificial variables a1 and a2 to the first and second constraints respectively. And since we are adding these artificial variables to these constraints, we'll also add them to the objective function. So let's rewrite the constraints first. So the first constraint will become 2x1 dash minus 2x1 double dash plus 5x2 plus x3 plus a1 equals to 12, 3x1 dash minus 3x1 double dash plus 4x2 plus a2 is equal to 11. Now these are the new constraints that we have, and again all these variables should be greater than or equal to 0. So x1 dash, x1 double dash, x2, x3, a1 and a2 should be greater than or equal to 0. Now we need to add a1 and a2 to the objective function as well. However, we don't want these two artificial variables to appear in the final solution because these two variables are artificial and do not have any physical meaning. So in order to avoid them from coming in the final solution, what we'll do is we'll assign them a coefficient such that it reduces the profit or the value of z, because the objective is to maximize z. So if the introduction of a1 is reducing z, then automatically it will be eliminated from the solution, and same with a2. So let's write the objective function. So maximize z equals to 3x1 dash minus 3x1 double dash plus 2x2 plus x3. Now we'll assign a coefficient which is a large number, that is m, to a1 and a2, and we want the impact to be negative on the profit or the value of z. So we'll do minus ma1 minus ma2. So this becomes our standardized form of the LP model, which we'll solve using the Simplex method, or specifically the Big M method. So now after step number 2, which is to standardize the problem, we'll move to step number 3, which is to create the Simplex table. I have noted the standardized LP model here in red. Now the first row of the Simplex table represents the contribution per unit, also represented as Cj, and this will have the coefficients of the variables in the objective function. So we have 3 minus 3, 2, 1, minus m, and minus m. The second row of the table indicates the variables in the problem for which the Cj components have been written in the first row. So x1 dash, x1 double dash, x2, x3, a1, and a2. Now below the second row of the table, the coefficients of the variables in the constraints are noted down. So let's do that for the first constraint. So 2x1 dash, so 2 will come in the first column, minus 2x1 double dash, so minus 2 in the second column, 5x2, so 5 in the third column, 1x3, a1 has a coefficient of 1 and a2 does not exist here, so this will be 0. For the second constraint, 3x1 dash minus 3x1 double dash, 4x2, there's no x3, there's no a1, and 1a2. Now there are some more columns to be added to this simplex table, which we will add after the next step of establishing a basic initial feasible solution. Now in order to establish the basic initial feasible solution, we'll put all the decision variables as 0. So x1 dash, x1 double dash, x2, x3 is equal to 0. So now if we put these as 0 in the constraints, we'll get a1 is equal to 12 and a2 is equal to 11. So a1 is equal to 12, a2 is equal to 11. So the non-zero variables are known as the basic variables. So let's add two more columns to the left hand side of the simplex table. The first column is known as basis and the second is the CB value. So the basis column will contain the basic variables, which are the non-zero variables, so a1 and a2, and the CB column will contain the coefficients of the basic variables in the objective function, so minus m and minus m. Now on the right hand side of the simplex table, we need to add another column which is known as the solution values column, and it is represented by B. This column will have the values of the basic variables in this current solution. So a1 is 12 and a2 is 11. So a1 is 12 and a2 is 11. So this completes our simplex table with the basic initial feasible solution. Now let's proceed to step number 5, which is to perform optimality test. Now after we have established the initial basic feasible solution, we need to check if this solution is optimal or not. So now two new rows need to be added to the simplex table. The first row is Zj. The elements in the Zj row represent the decrease in the value of the objective function or profit, which will result if one unit of the variable in the jth column is brought into the solution. And Zj values for jth column are obtained by adding the products of the elements under that column with the corresponding CB values. So minus m into 2 plus minus m into 3. So this becomes minus 2m minus 3m. So minus 5m. Minus 2 into minus m becomes 2m. Minus 3 into minus m becomes 3m. So 2m plus 3m is 5m. Minus m into 5 becomes minus 5m. Minus m into 4 becomes minus 4m. So this becomes minus 9m. 1 into minus m is minus m. 0 into minus m is 0. So this becomes minus m. 1 into minus m again is minus m. And for column A2, again 0 into minus m is 0. 1 into minus m becomes minus m. For column B, minus 12m plus minus 11m. So this becomes minus 23m. Next we have to add another row, which is Cj minus Zj, which is also known as the net evaluation row. And this row is obtained by subtracting column wise the Zj values from the Cj values. So 3 minus minus 5m becomes 3 plus 5m. Minus 3 minus 5m. 2 minus minus 9m becomes 2 plus 9m. 1 minus minus m becomes 1 plus m. Minus m minus minus m becomes minus m plus m, which is 0. Minus m minus minus m becomes minus m plus m, which is again 0. Now the values in the row Cj minus Zj need to be evaluated to determine if the current solution is optimal or not. In case all the values are negative or 0, the current solution is optimal. However, in case any element is positive, then the solution is not optimal and there is scope for improvement. So here we have plus 5m plus 9m. So definitely we have positive values. So this solution is not optimal. Now let's proceed to the next step, which is step number 6, which is to iterate towards the optimal solution. Now since we have positive values for the row Cj minus Zj, which indicate that the solution can be improved further, we observe the values of Cj minus Zj for different columns and mark the column with the maximum positive value. So here 9m is the biggest, so we'll mark this column, and this column is known as the key column. And so the variable in that column becomes the entering variable or the incoming variable. So x2 is the incoming variable here. Now next we have to find the departing variable or the variable which will be replaced by x2. So we have to add another column theta. Now the value for the column theta are obtained by dividing the values in column B with the corresponding elements of the key column. So 12 divided by 5 and 11 divided by 4. 12 divided by 5 is 2.4 and 11 divided by 4 is 2.75. Now the row containing the minimum non-negative ratio is chosen as the key row. So here the first row is the key row because 2.4 is smaller than 2.75. So the variable in the first row now, which is A1, becomes the outgoing variable. So now after we have selected the key column and the key row, a revised simplex table providing an improved solution can be developed. First, the incoming variable now replaces the departing variable, and the coefficient of the incoming variable in the objective function is entered in the CB column. So let's do that. So the incoming variable is x2 and the coefficient of x2 in the objective function is 2. Now the element at the intersection of key row and key column is the key element. So here 5 is the key element. Now we need to make this key element as 1. So we have to divide the key element by itself to make it 1. And since we are dividing this element by 5, we have to divide all the other elements in this row also by 5. So let's do that. So 2 divided by 5 minus 2 divided by 5, this is 1. 1 divided by 5, 1 divided by 5, 0 divided by 5 is 0, and 12 divided by 5 is 12 divided by 5. So let me replace this row with the new elements. Now let's move to the next row, which is A2. So here the element at the intersection of row A2 and the key column has to be made 0, and that will be done by subtracting a multiple of the reduced key element from the element in the other row. Now the same multiple has to be multiplied by all the reduced elements of the key row and subtracted from the corresponding elements of the target row. Also, the variable in the basis column and its coefficient in the CB column remain as it is. So basically what we have to do is 4 minus 1 into x is 0. So 4 minus 1x is 0, or x is equal to 4. So basically 4 minus 1 into 4, which will become 0. Now for this one, the first column, 3 minus 2 by 5 into 4. So 3 minus 2 by 5 into 4. So this is 3 minus 8 by 5. 5 is the LCM. 5 3s are 15 minus 8. So this is 7 by 5. Minus 3 minus 2 by 5 into 4. Minus 3 minus 2 by 5 into 4. So this is minus 3, minus minus will become plus, 8 by 5. 5 is the LCM. So 3 5s are 15. So minus 15 plus 8 minus 7 by 5. Now column x3, 0 minus 1 by 5 into 4. So this is minus 4 by 5. For A1, 0 minus 1 by 5 into 4, this is the same as x3, so this becomes minus 4 by 5. For A2, 1 minus 0 into 4, so 0 into 4 is 0, so this will be 1. For column B, 11 minus 12 by 5 into 4, so 11 minus 12 by 5 into 4, so this is 11 minus 12 4s are 48 by 5. 5 is the LCM. 11 5s are 55 minus 48. So this is 7 by 5. So let me replace this row with the new elements. So this is our new and improved solution. So let's now move to step number 7, which is nothing but repeating of step number 5 and 6 till we obtain an optimal solution. So now that we have this improved solution, we should perform the optimality test on it. So let's do that. 2 into 2 by 5 becomes 4 by 5 plus minus m into 7 by 5. So 4 by 5 minus 7 by 5m. 2 into minus 2 by 5 becomes minus 4 by 5 plus minus m into minus 7 by 5. So minus 4 by 5 plus 7 by 5m. 2 into 1 is 2. 2 into 1 by 5 is 2 by 5. plus minus m into minus 4 by 5 plus 4 by 5 m. 2 into 1 by 5 is 2 by 5 plus minus m into minus 4 by 5, so plus 4 by 5 m. 2 into 0 is 0, minus m into 1 is minus m. 2 into 12 by 5 becomes 24 by 5 plus minus m into 7 by 5, so minus 7 by 5 m. Now let's find out the values for Cj minus Zj. So 3 minus 4 by 5 minus 7 by 5 m. 3 minus 4 by 5 minus 7 by 5 m. This is 3 minus 4 by 5 plus 7 by 5 m. So we'll keep the component containing m as it is. So this becomes 5 is the LCM. 5 3s are 15 minus 4 plus 7 by 5 m. So 15 minus 4 is 11 divided by 5 plus 7 by 5 m. So 11 by 5 plus 7 by 5 m. For the next column, minus 3 minus 4 by 5 plus 7 by 5 m. So minus 3 minus 4 by 5 plus 7 by 5 m. So minus 3 minus, again minus minus becomes plus, 4 by 5 plus, no, this becomes minus, plus minus minus 7 by 5 m. So 5 is the LCM. Minus 15 plus 4 minus 7 by 5 m. So this is minus 11 by 5 minus 7 by 5 m. So minus 11 by 5 minus 7 by 5 m. 2 minus 2 is 0. 1 minus 2 by 5 plus 4 by 5 m. So 1 minus 2 by 5 plus 4 by 5 m. This is if we have the bracket, so this will become 1 minus 2 by 5 plus minus minus 4 by 5 m. We leave the m component as it is, so this becomes 5 as the LCM. 5 ones are 5 minus 2 minus 4 by 5 m. So this is 3 by 5 minus 4 by 5 m. So 3 by 5 minus 4 by 5 m. Let me delete all this calculation to make some space for further calculations. So minus m minus 2 by 5 plus 4 by 5 m. So this is minus m minus 2 by 5 minus 4 by 5 m. So we'll club m together. So minus m minus 4 by 5 minus 2 by 5, sorry, minus 4 by 5 m. So this becomes 5 as LCM. Minus 1 into 5 minus 5 minus 4 m minus 2 by 5. So this becomes minus 9 m by 5 minus 2 by 5. So minus 9 by 5 m minus 2 by 5. Minus m minus minus m becomes minus m plus m, which becomes 0. So now that we have calculated the values for Cj minus Zj rho, we need to evaluate these values to assess whether this solution is optimal or not. So if we have any positive value, that means the solution is not optimal and it can be improved further. So here we have this value for column x1 dash as positive. All the remaining are negative. So let's mark this column as our new key column. Let me delete this calculation. So x1 dash is our new entering variable. Now we have to find the departing variable, for which we have to calculate the value for column theta. So we have to divide the values in column B with the corresponding values in the key column. So 12 by 5 divided by 2 by 5. 12 divided by 5 into 5 divided by 2. So this is 6. 7 by 5 divided by 7 by 5 is 1. So the minimum non-negative ratio is 1. So this becomes our key row. So A2 is the outgoing variable, while x1 dash is the incoming variable. So now that we have established the key column and key row, a revised simplex table providing an improved solution can be developed. So first, the incoming variable now replaces the outgoing variable, and the coefficient of the incoming variable in the objective function is entered in the CB column. So here A2 is the outgoing variable while x1 dash is the incoming variable. So let's do that. So x1 dash, and the variable has a coefficient of 3 in the objective function, so CB value is 3. The element at the intersection of key row and key column will be the key element, so here 7 by 5 is the key element. Now we have to make this 1 by dividing it by itself, and so we have to divide all the other numbers in this row by 7 by 5. So let's do that. 7 by 5 divided by 7 by 5 will become 1. Minus 7 by 5 divided by 7 by 5 will become minus 1. 0 divided by 7 by 5 will be 0. Minus 4 by 5 divided by 7 by 5. So minus 4 by 5 into 5 by 7. 5 get cancelled, so minus 4 by 7. Minus 4 by 5 divided by 7 by 5, again same, minus 4 by 7. 1 divided by 7 by 5 becomes 5 by 7. And 7 by 5 divided by 7 by 5 becomes 1. Let me replace this row with the new numbers. Now let's move to the next row, which is row x2. So here we have to make the element at the intersection of the x2 row and the key column as 0. And we have to do that by subtracting a multiple of the reduced key element from this element. And now the same multiple has to be multiplied by all the reduced elements of the key row and subtracted from the corresponding elements in the target row. So let's do that. So 2 by 5 minus 1 into x is 0, or x is equal to 2 by 5. So basically 2 by 5 minus 1 into 2 by 5. So this becomes 0. Minus 2 by 5 minus minus 1 into 2 by 5. So minus 2 by 5 minus minus 1 into 2 by 5. Minus 2 by 5 minus minus is plus 2 by 5. So this becomes 0. 1 minus 0 into 2 by 5. So 0 into 2 by 5 will be 0. So this remains 1. 1 by 5 minus minus 4 by 7 into 2 by 5. So 1 by 5 minus minus 4 by 7 into 2 by 5. So 1 by 5 plus 8 by 35. So 35 is the LCM. 7 plus 8, 15 by 35. 5 3s are 15. 5 7s are 35. So this is 3 by 7. Now again for column A1, 1 by 5 minus minus 4 by 7 into 2 by 5, which is same as column x3. So this also will be 3 by 7. For A2, 0 minus 5 by 7 into 2 by 5. 0 minus 5 by 7 into 2 by 5. 5 gets cancelled. Minus 2 by 7. For column B, 12 by 5 minus 1 into 2 by 5. So 12 by 5 minus 1 into 2 by 5 is 2 by 5. So 2 by 5. LCM is 5. 12 minus 2 is 10. 5 2s are 10. So this is 2. Let me replace this row with the new elements. So this is our new and improved solution. Let's perform triviality test. So 2 into 0 plus 3 into 1 is 3. 2 into 0 plus 3 into minus 1 is minus 3. 2 into 1 is 2. 2 into 3 by 7 is 6 by 7. Plus 3 into minus 4 by 7. So 6 by 7. Plus minus will become minus. 4 3s are 12 by 7. So 6 minus 12 is minus 6. So this is minus 6 by 7. 2 into 3 by 7 plus 3 into minus 4 by 7. This is the same as column x3. So this is also minus 6 by 7. 2 into minus 2 by 7 plus 3 into 5 by 7. So 2 into minus 2 by 7 plus 3 into 5 by 7. So minus 4 by 7 plus 15 by 7. 7 is the LCM. Minus 4 plus 15. So this is 11 by 7. And then 2 into 2 is 4 plus 3 into 1 is 3. So 4 plus 3 is 7. Now let's find out the values for Cj minus Zj. So 3 minus 3 is 0. Minus 3 minus minus 3 becomes minus 3 plus 3, which is 0. 2 minus 2 is 0. 1 minus minus 6 by 7. So 1 minus minus 6 by 7. This becomes 1 plus 6 by 7. So LCM is 7. 7 plus 6, 13 by 7. Minus m minus minus 6 by 7. So minus m plus 6 by 7. Minus m minus 11 by 7. Minus m minus 11 by 7. So here again we have a positive value for column x3. So x3 now becomes our key column. Let's find the value of theta. So 2 divided by 3 by 7. So 2 into 7 by 3. So 14 by 3. And 1 divided by minus 4 by 7. So this is 1 into minus 7 by 4, which is minus 7 by 4. Now we have to choose the minimum non-negative ratio, which is 14 by 3, because minus 7 by 3 is not non-negative. So this becomes our key row. So x2 is the departing variable, while x3 is the incoming variable. And the element at the intersection of key column and key row will be the key element. So 3 by 7 here is the key element. Now first let me replace x2 with x3 and 2 with the coefficient of x3. So x3, and the coefficient for x3 is 1. So CB value is 1. Now let's divide all these numbers by 3 by 7. So 0 divided by 3 by 7 is 0, 0 divided by 3 by 7 is 0, 1 divided by 3 by 7 is 7 by 3, 3 by 7 divided by 3 by 7 is 1, 3 by 7 divided by 3 by 7 is 1, minus 2 by 7 divided by 3 by 7, so minus 2 by 7 into 7 by 3, so minus 2 by 3, 2 divided by 3 by 7, so 2 into 7 by 3, so 14 by 3. Let me replace this row with the new elements. Now let's move to the next row. So here we have to make this element minus 4 by 7 as 0. So minus 4 by 7 minus 1 into x is 0, or x is equal to minus 4 by 7. So here we get minus 4 by 7 minus 1 into minus 4 by 7. So this becomes minus 4 by 7 plus 4 by 7, or this will be 0. So for x1 dash, 1 minus 0 into minus 4 by 7. So 0 into minus 4 by 7 is 0. So this remains 1. For x1 double dash, minus 1 into 0 into minus 4 by 7. So this will remain minus 1. For x2, 0 minus 7 by 3 into minus 4 by 7. So 0 minus 7 by 3 into minus 4 by 7. So this is minus minus will become plus. So 4 by 3. For a1, again this is the same as x3, so this will also become 0. For a2, 5 by 7 minus 2 by 3 into minus 4 by 7. So this is 5 by 7. Minus minus is plus, and plus minus is minus. 4 2s are 8, 7 3s are 21. So LCM is 21, 7 3s are 21, and 3 5s are 15, minus 8. So this is 15 minus 8 is 7 by 21, or 1 by 3. So this is 1 by 3. For column B, 1 minus 14 by 3 into minus 4 by 7. So minus minus plus, 1 plus, now 7 2s are 14, so 4 2s are 8 by 3. 3 is the LCM, 3 plus 8, so this is 11 by 3. So this is 11 by 3. Let me replace this row with the new elements. So now that we have the revised solution, let's find the value of zj to perform the optimality test. So 1 into 0 plus 3 into 1, 3. 1 into 0 plus 3 into minus 1, this is minus 3. 1 into 7 by 3 plus 3 into 4 by 3. So 7 by 3 plus 3 into 4 by 3. So 3 gets cancelled. So this is 7 by 3 plus 4. So 3 is the LCM. 7 plus 4 3s are 12. So this is 19 by 3. 1 into 1 is 1. Again 1 into 1 is 1. For A2, 1 into minus 2 by 3. So this is minus 2 by 3 plus 3 into 1 by 3, which is 1. So 3 is the LCM, minus 2 plus 3, this is 1 by 3. And for B, 1 into 14 by 3 is 14 by 3 plus 3 into 11 by 3 is 11. So 3 is the LCM, 14 plus 33. So this is 47 by 3. Now let's find Cj minus Zj. So 3 minus 3 is 0. Minus 3 minus minus 3 becomes minus 3 plus 3, which is 0. 2 minus 19 by 3. So 3 is the LCM. 6 minus 19. This is minus 13 by 3. 1 minus 1 is 0. Minus m minus 1. Minus m minus 1 by 3. So here, as we can see, all the values of Cj minus Zj are either 0 or negative, which means that the solution obtained is optimal. Let me clean up this calculation. So here we have x3 equals to 14 by 3 and x1 dash equals to 11 by 3. So x3 is equal to 14 by 3, x1 dash is equal to 11 by 3, and the value of z, or the objective function, is equal to 47 by 3. Now since x1 double dash and x2 double dash are not in the basic variables here, so these two are zeros, so we have x1 double dash equals to 0 and x2 is also equal to 0. This is 11. Now in the beginning we had considered x1 dash minus x1 double dash equals to x1. x1 dash is 11 by 3 and x1 double dash is 0. So x1 is equal to 11 by 3. So we have x1 equal to 11 by 3, x2 equal to 0 and x3 equal to 14 by 3, and the value of z is 47 by 3. So this is the optimal solution for the problem at hand.